Hello everyone, welcome to another lesson in highway engineering. To those who are new in this channel, I am Engineer J. I am a civil engineer and I am also currently teaching as an engineering professor. Now, I have here a new topic in highway engineering. We have this parabolic curve. Now, in our previous discussions, we learned how to compute the properties of horizontal curves, such as we learned about simple curve, compound curve, reverse curve, and lastly we have spiral curve. And these curves are in terms of circular curve. But in this video, we will now be dealing with the profile curvature or profile properties of our roadway, and that we have this vertical curve, which is in the form of a parabolic curve. Now, as what I have mentioned always, that it is necessary that we design our curves properly so that we would ensure the safety of the road users. We need to ensure na our slope or the slope of our road is not that too steep, especially when you are overtaking. It is necessary that we can see the roads on the other lane to avoid any accidents or to avoid collision. And that is why we need to consider sight distances when we are computing or when we are designing roads. And that would also include properly design of the vertical aspect of our highways. And what is parabolic curve, by the way? So parabolic curve, this is most commonly used design, especially when if you are designing in a very mountainous area, diba? And that to make sure that we avoid too much excavation, so we designed our road according to the geophysical characteristic of the environment. Okay? And that we experienced steeper road, diba? We experienced a slopey road, and that road is actually designed parabolically. Okay, and that's an example of a parabolic curve. As you can see, this is an example of a sag curve. Okay, and this is an example of a summit curve. Okay, as what you can see in the picture. So we have two types of parabolic curve. We have symmetrical curve and a non-symmetrical parabolic curve. So later I'll discuss to you the difference between these two parabolic curves. Now, the curves used in a vertical plane to provide a smooth transition between the grade lines of highways and railroads are called vertical curves. When moving along the road in the direction of increasing roadway stationing, the first of the grade lines that will be encountered is called the back tangent, and the following grade tangent is what we call the forward tangent. So basically, this is an example of a parabolic curve. So this first tangent that you experience, so tangent at PC, or the beginning of our parabolic curve, is what we call the back tangent, and this curve which is in tangent at the point of tangency or the end of our parabolic curve is what we call the forward tangent. So this is an example of a summit curve. So we have a highest point on our curve. Okay, so these are the properties and the elements of our parabolic curve. Now we have these properties of parabolic curve that we need to remember. Now the length of parabolic curve L is the horizontal distance between PI and PT. So when we are always referring with the length of parabolic curve, that is always the horizontal distance. Okay, not the curve distance. It is always the horizontal distance. The curve is midway between PI and the midpoint of the chord from PC to PT. Now for symmetrical parabolic curve, we have our PI. PI is the intersection between the two tangent lines. PI is located between PC and PT, and we have L over 2 from PC and L over 2 from PT. So PI is located midpoint of the horizontal distance from PC to PT. Now, if we draw the grade diagram, now by the way, this grade diagram here is one of the approach in computing for the elements of our parabolic curve. Now, grade diagrams can be useful in computing for the vertical distances. Now, according to number 3, the vertical distance between any 2 points on the curve is equal to the area under the grade diagram. The vertical distance C is equal to the area. So, for example, if we want to compute the vertical distance between, let's say, this our A and B, and that we have C, you just need to compute the area between that 2 points, and this area here equals to the vertical distance. So later I'm gonna teach you on how to draw the grade diagram of our parabolic curve. Number 4, the grade of the curve at a specific point is equal to the offset distance in the grade diagram under that point. The grade at point Q is equal to GQ. Now, this grade diagram here is actually the slope of our curve. Now, by the way, this grade here is another term for slope, but that grade is in terms of percentage. So if we have G1 is equal to 4%, so this 4% here means 4 over 100. That means in every 100 meter horizontal distance, we have a 4 meter vertical height, and that our slope would be this one, this angle here, theta. Okay, so we have G1 here is equal to 4%. Okay, or that is 4 over 100. So 100 horizontal, 4 meter vertical, and that we have 4% grade. Now, our grade diagram here is just basically, if we have grade or slope at PC equal to G1, so that is just the vertical height at PC. This one is G1. And since at PT we have G2, that means we have G2, since that has a negative grade, that means we have to go down. Okay, this G2 here, that is the vertical distance, and that is equivalent to the grade at PT. So if we have Q here, that means this height here is our GQ. Okay, or that is the slope at point Q. Okay, so that's how you draw the grade diagram. Now, the angle here at the intersection of two tangents is just basically G1 minus G2. Now, if our G1 minus G2 is positive, that means we have summit curve. Summit curve is when we have our parabolic curve concave downward. So if we have a frowning curvature. Now, if G1 minus G2 is negative, that means we have a sag curve or a smiling curvature of our parabolic curve. Okay? And the length of the parabolic curve refers to the horizontal distance. Hence, the stationing is measured not along the curve but horizontal line. Since again, our length is always measured horizontally for parabolic curve, and so is the stationing of our parabolic curve. So we station our parabolic curve always horizontally. Okay? So these are some of the reminders when we are referring to symmetrical parabolic curve. Now, to compute for the elements of the curve, so we have this formula. Now, h here is the distance from pi to the midpoint of our curve, and that we have the formula L over 8 times G1 minus G2. Now, to compute for the highest or the lowest point of our curve from PVC, so if, for example, this is our highest point of our curve, and to compute for S1, we just need to use this formula. We have G1, the grade 1 times L over grade 1 minus grade 2, okay? And then for S2, which is the location of the highest or the lowest point from PT, so we will be using G2 on the numerator instead of G1. Okay, now we also have rate of change per meter station. We have R is equal to G1 minus G2 over N. So again, you can use this formula to compute for the properties of our parabolic curve, or you can just use the grade diagram, which I guess the easier, okay, compared to the formula method. Okay, so let's try to solve example. And then we have this first example. We have a symmetrical vertical summit curve with tangents of positive 4% and negative 2%. The allowable rate of change of grade is 0.3% per meter station. Stationing and elevation of PT is at 10 plus 020 and 142.63 meters respectively. The first question is compute the length of the curve, compute the distance of the highest point of curve from PC, and compute the elevation of the highest point of curve. So the first thing we do here is, of course, we draw our curve. Now we have this symmetrical vertical curve. This is symmetrical since our tangent, our back tangent is in 4%, that's positive, and we have forward tangent which is negative, and that is we have a downward slope of our tangent. So we will be computing this problem by using both the formula application and the grade diagram. So the first thing we do here is to draw the curve. So we have this curve. Again, this is a summit curve. We have a PC and we also have a PT here. Okay, or we can also say PVC and PVT. So it's up to you. Now, we have grade for our back tangent, which is 4%, and grade for our forward tangent, which is negative 2%. Okay, so, and we also have given that our R is equal to 0.3%. That is per meter station. Now, again, our stationing is every 20 meters. Okay, and then we have the stationing and elevation of PT. So this PT here is 10 plus 0.20 and the elevation is 142.63 meters. Okay, so we have to compute the length of the curve. So the length of the curve is the horizontal distance from PC to PT. So this one. So how are we going to compute for L? Now we have given rate of change. Now we know that rate of change is equal to G1 minus G2 over N. So we can compute the number of stations, and that we have 0.3% is equal to our G1 is 4%, and then we have minus negative 2% over N. So we can now compute the number of stations, and that is we have 20 stations. Okay, to compute for L, we just simply need to multiply 20 meters times 20 station. That would give us L is equal to 400 meters. So our L here is equal to 400 meters. Okay, so this is our question number 1. Okay, answer for question number 1. Now for second question, we are asked to compute the distance of the highest point of curve from PC. So let's assume that our highest point is this point here. Let's say this is our highest point, and let's say our highest point is this point here. So we have the distance from PC, which is S1. Okay, and we know that the formula for S1 is equal to G1L over G1 minus G2. So therefore we have S1 is equal to, our G1 is 4%. You can express that into decimal. So we have 0.04 times L, which is 400, over 0.04 minus negative 0.02. So our S1 is basically equal to 266.667 meters. So the location of the highest point, let's say this is our summit, is equal to 266.667 meters from PC. Or you can just use the grade diagram. So if you want to draw the grade diagram, basically you just need to plot that on our diagram. So to plot, we start at PC. Now we know PC has a grade of 4%, so we go up, that is positive, that is 0.04, and then at PT we have negative 0.02, so we go down, so we have here 0.02, this is negative. Then we connect the point. So our highest point is basically at the point where we have 0 grade. So this is the point where our grade is equal to 0. Okay? So, our goal here is to compute this length S1. Okay? So, we have incorrect assumption by the way. So, our summit should be at this point. So, therefore, we have incorrect curve. So, to compute for S1, we will just be using ratio and proportion, in which we can have the relationship which is 0.04 over S1 is equal to 0.02. Now again, this length here is 400 minus S1, correct? So therefore, we have over 400 minus S1. So by further simplifying, we have S1 here equals to 266.667 meters. So we have the same answer using the formula. Okay, so this is the location of the highest point or the summit from PC. Okay, for our third question, we are asked to compute the elevation of the highest point of curve. So we are asked to compute the height or the elevation of this point, which is our summit. Now, again, from the properties of symmetrical curve, now looking at the grade diagram, we know that the vertical distance between 2 points on our curve is equal to the area between 2 points in our grade diagram. Okay, so therefore, the distance between PT, let's say this is our A, let's say this is our C, the vertical distance between these 2 points is equal to the area between the 2 points in our grade diagram. So therefore, this area here. So by computing this area, we would also compute the value of C, which is the difference in elevation between A and PT. So we will refer our C from PT because we have known elevation at PT. So if we get the value of C, then we add that to 142.63 meter, and that would give us the elevation at A. Okay? So we have to compute the area of our grade diagram. We have C is equal to 1/2 times 0.02 times 400 minus S1, okay? And that is, we have C is equal to 1/2 times 0.02 times 400 minus, now we already know that the value of S1 is 266.667. This would give us the value of C, which is 1.333 meters. So to compute for the elevation of A, we just need to add the elevation of PT. We have 142.63 plus C, which is 1.333. This would give us 143.963 meters. So this is the elevation of the highest point of our curve. Okay, so that's how you use grade diagram in computing for the elevation. Now, what if we try to use formula to compute for the elevation of the summit? Okay, so we will be computing first the value of H, this one, and then we use the square property of parabola, in which the relationship between the vertical offset from tangent to any point of the curve is proportional to the square of the distance. So that means if we have H, the vertical offset, so H over, now we know that the distance between H to the PT is just 1/2 of the length. That is, we have 400 divided by 2, okay, or this is 200 because this is symmetrical parabolic curve. Okay, so therefore that is H over 200 squared equals to, let's say at the summit point to the tangent, the vertical offset, let's say that's Y. So we have Y over, the distance is S2 or 400 minus S1 from PT. So we have here S2 squared. Okay, so that is the relationship of the distances using parabola, or that is the other term for that is we have the square property of parabola. Okay, so we have to compute for h. Now we know that the formula for h is equal to L over 8 times G1 minus G2. Okay, so we have h is equal to L is 400 over 8 times G1 is 0.04 minus negative 0.02. We have negative 0.02. So we have h is equal to 400 over 8 times 0.04 plus 0.02. And this would give us h equals to 3. Okay, so we have 3 meters from PI to the curve. Okay, this is 3 meters. So we can now compute y. So we have 3 over 200 squared equals to y over S2 here is basically 400 minus S1, and that would give us 133.333. So we have 133.33 squared. This would give us y equals to 1.333. So how are we going to compute for C? Okay, so we know that C is from PT to the highest point. Let's say that's our C. So we can isolate this triangle. Okay, so we have this triangle. We have this length which is 133.333. We have y and c if this is our curve. Now we just need to compute this total vertical height by using ratio and proportion. Now we know that G2 is negative 2%, or that is equivalent to 2 over 100. So 2 over 100, that is equivalent to, let's say this is our V. Okay, so we have 2 over 100 is equal to V over 133.333. Okay, or just basically V is equal to the length times the grade. Okay, so that means we have the length is 133.333 times the grade, which is 0.02. Okay, you just get the vertical height, which is 133.333 times 0.02. This would give us 2.667. So we can now compute C by just subtracting y from V. So we have V minus y. This would give us 2.667 minus 1.333. So we have C is equal to 1.333 meters. So we can now compute the elevation at the highest point. Again, that is point A. Elevation of highest point, which is equal to the elevation at PT plus C. This would give us 142.63 plus C. We have 1.333. So therefore, the answer would be 143.964 meter. So we have the same answer using the grade diagram, but this is quite too long compared to grade diagram, which has expedite the procedure. Okay, so it's up to you on which procedure you will be using. You can use either the grade diagram, or you can use the parabolic properties or the formula. Okay, and that ends our example number 1. So let's proceed to our second example. Now we have the second example. We have a negative 6% grade and a positive 2% grade intersect at station 12 plus 200, whose elevation is at 25.632 meters. The two grades are to be connected by a parabolic curve, 160 meter long. Find the elevation of the first quarter point on the curve. So to better analyze the problem, we need to draw the parabolic curve. We have this curve, which is a sag curve, because we have negative 6% grade for our back tangent, and we have 2% grade in our forward tangent. And then, according to the problem, these two tangent intersects at 12 plus 200. So the intersection, or at the since this is symmetrical curve, therefore the intersection is at midpoint between PC and PT. Okay? So this is our PI. And PI again has elevation of 25.632 meters. So this is the height or the elevation at this point. And the station is 12 plus 200. So the question is, find the elevation of the first quarter point on the curve, and then the length of the curve is 160 meter. Okay? So we have 80 meters between PC and PI and 80 meters from PI to PT. Okay, so we are asked to compute the quarter point. So quarter point, we divide 160 by 4. So this would give us 40 meter. So our first quarter point is at 40 meters from PC. So at this point. So we will be computing the elevation of this point. So we have this 40 meters. So we can use grade diagram to compute for the elevation. We have at PC we have negative 6%. So we go down. So this is negative 0.06, and at PT we have 0.02. That's positive. So we have here 0.02. So we connect. So this is the grade diagram. So we are asked to compute the elevation at this point. So by computing this area, we can compute the difference in elevation between PC and the quarter point. Let's say this quarter point is point A. So we can compute C. So we can compute the area. However, we are lacking of values here. We have this S1 and S2, in which S2 is 160 minus S1, correct? So by ratio and proportion, we have 0.06 over S1 equals to 0.02 over 160 minus S1. So we would have the values of S1 here equals to 120 meters. So we have this distance 120 meters, and we have S2 here equals to 40 meters. Okay? So to compute for the area, we will be needing this height here. Let's say this height is Y. So we have ratio and proportion again. We would have 0.06 over 120 equals to Y over, now this height or this distance is equal to 120 minus 40, because we know that our Y is located 40 meters from PC, correct? So we have 120 minus 40, this would give us 80 meters. So we have Y over 80. So we would have the value of Y equals to 0.04, and this denotes the grade at point A, because as we all know, the grade is the vertical distance on our grade diagram. So Y here is equal to 0.04. So we can now compute the area by, let's say this is our area 1. So our area 1 here is the area of a trapezoid. We have 1/2 times 40, that's the length, times 0.04 plus 0.06. So we disregard the sign of 0.06 because we are computing here for the area. Okay, so we have area equals to, and this also equals to C, correct? Or the difference in elevation between PC and point A. So we have 2 meters. So going back to the parabolic curve, our C here is 2 meters. So we will need the elevation at PC, so that once we have the elevation of PC, we subtract the value of C to compute for the elevation of A. Okay, however, we do not know yet the elevation of PC. Now, however, we have the elevation of PI, which is 25.632. So we can compute PC by having this triangle. So we have this triangle. This is our PC. This is our PI. which is 25.632. Okay, and this is, of course, is 80 meters. And we have the grade, which is 0. We have negative 6%. So we can compute V here. V is the total distance from PC to PI. That's the vertical height. So we can compute V here by multiplying 80 and the grade. We have 0.06. So this would give us V is equal to 4.8 meters. So V here is 4.8 meters. So again, we multiply because this is basically a ratio and proportion in which 6% is equivalent to 100 meter horizontal and 6 meter vertical. So that is 6 over 100 equals to V over 80. So that would give us V is equal to 6 over 100 times 80. Or we know that 6 over 100 is 0.06 and times 80. Now we have computed the value of V, so we can now compute the elevation of PC by adding the elevation of PI and the V. So we have the elevation of PI, which is 25.632 plus 4.8. This would give us 30.432 meters. So we can now compute. So we have the PC elevation, which is 30.432. So to compute for elevation at A, we just subtract C here, and that would give us elevation of A is equal to elevation of PC minus C. Correct? So we have elevation of A is equal to 30.432 minus 2 meters. This would give us 28.432 meters. So this is now the answer for the elevation of point A. And that ends our discussion on parabolic curves. So if you have questions, you can comment it down. Thank you guys for listening, but please don't forget to subscribe to my channel and hit the notification bell. Thank you and see you on my next video.